Recording is rolling. It's Friday, January 30th. We're going to focus on the special puzzles today. I'll do as many of these in class with you guys as I can. So, like normal, whatever we do in class is what I'll eventually pick up from you guys and score. Okay. You guys turned in your spring oscillation lab from yesterday. Quick recaps of that. You guys had this type setup going on right here. Okay. Now, at this point, I gave you the formula ahead of time, so you could solve for K in terms of the time for oscillation and whatever mass you attach. Right, so a little bit backwards in the pendulum situation, where the pendulum situation you had you guys to sort of drive the formula, which is L over G. But this one, something you guys did is you lowered it to equilibrium and you solved K from a Hooke's law point of view. You let it oscillate, okay, and solved K from a oscillating point of view. Right, which was an FRQ just a few years ago. And then you guys made 4 graphs. A lot of you guys had almost finished these by the end of class, but just needed to finish these last night. So this is the answer to those 4 graphs for what you got. Looking at the data from all the classes that did this lab yesterday throughout the day, look pretty spot on. It's, yeah, that's what you should have gotten. Pretty much like that. All right, so let's go on to these puzzles. Oh, yeah, one more detail here. Guys, what are you guys going to have done by the time you guys come to class on Wednesday? Yeah, 80 classroom. All right, so these puzzles here. All right, everybody got some paper out. Okay, let's try number 5 here. Number 5. Ooh, I like this one because it's giving us some kind of position versus time. Actually, position versus time. Guys, you guys think that graph there is basically that graph right there? Yeah. So it's, yeah, well, you guys, it's true. A system consisting of a 1.2 kilogram object attached to a spring oscillates on a horizontal surface with negligible friction. So if I draw this to match the picture, they're talking about this situation going on. Okay, so we got spring, we got a mass. Now they told us this mass is equal to 1.2 kilograms. Guys, everybody's write this down?
Yes.
What's on this? And there's no friction.
I keep going.
Guys, if there's no friction on this horizontal surface that's oscillating back and forth, could that be physically identical, like the same time period and so on, as if I just had it going vertical like yesterday? Yep. Yeah. Right. So it'd be the exact same time period to your lab yesterday. Okay, no difference. The mass of the spring is negligible. Yeah, always one of those details they mentioned, right, to make this an ideal scenario. The graph of position versus time is shown in the figure. So you guys can see this maybe oscillating back and forth. You know, have little oscillating arrows going on right here. It's like this. Right. It's going like back and forth. Okay, you guys that. Okay. They show position versus time. Okay. Oh, actually, here, we got some numbers on this graph, so maybe I'll just go ahead and mark that here. Right, so they're saying all the way up here is, I'll call it X max equals what is it, 4 centimeters? Yeah. So positive 4 centimeters. Okay. Next min is negative 4 centimeters. So that can be right here. Okay. So this is X min equals negative 4 centimeters. Okay. So guys, how do you set this up? What's defined as the equilibrium position? Yeah, 0 centimeters. So this could be 0 centimeters, could be the equilibrium. It's that. It's going back and forth. Okay. Yeah, they could have defined the numbers however they wanted to. They could have defined 0.0 over here and what okay. Maybe guys, could they have done this? Could they say this is a position 10, 14, and 18? Could they have done that? Yeah, they can make the position whatever they want. Express the position of the object as a function of time. Ooh, position is a function of time. Well, since you guys have these AP equations to work with, maybe I'll refer to that. I have a poster version I pointed out to you guys the other day too. They wrote your notes, but here's the AP version. So let's start with that. So we got x here. I'll make it look like a function. X is a function of time. So position is a function of time. It's equal to a times. Now, if we wanted to map this exactly, should I choose the sine or the cosine version for this exact picture right here? Because yeah, my default was cosine, but what do you guys say for this one? What do you think?
Is it sine because it starts from the middle?
Yes, exactly right. Yeah, you guys see it actually starts at the equilibrium point. Right. So maybe maybe we already have it set in motion. It's already going, okay? And we happen to start tracking at time 0, where it happens to be going through the equilibrium. Yeah. So for that reason, let's go ahead and use sine. Okay. Okay. And then we need 2 pi times the frequency, and then time is the independent variable. Alright, so this is position as a function of time.
Yeah, we get it for both.
Okay. This is your time is an independent variable. The tick tock kind of tick along. Okay. Here's the frequency. Okay. Guys, do you guys remember 2 pi f? Actually, yesterday or the other day, I was grouping this together. What was calling 2 pi f? Angular frequency. Yeah, right. Now, I'll just go ahead and list it out this way today so you can see it different ways. Okay. Guys, what do you think this A stands for? Amplitude. Okay. All right, so we got the format of the equation right there. We know what everything stands for. Okay. Now we have to match what's what to make exactly this curve right here. Let's try it out. So I'll go position as a function of time is equal to. Okay. Guys, what do you think the amplitude is in this case? 4 centimeters. Yeah, 4 centimeters. We give it 0.04 meters if you like. I'll call it 4 centimeters times sine of Well, okay, I'm going to put the 2 pi in here. Okay, because what is the frequency? Or how could you get frequency? Exactly, reciprocal of the time period. Okay, well, let's look on this graph here. Guys, could you go from crest to crest? Is that one way you could get like one complete oscillation? Okay. So right here, this looks like 0.1 seconds. This looks like 0.5 seconds. Okay. Ooh, guys, from 0.1 to 0.5 seconds, what's the time interval? 0.4 seconds. Okay. Or alternately, you could go from here to here, one full S shape. Okay, that's also 0.4 seconds. It doesn't matter how you measure it. You'll get 0.4 seconds regardless. So 1 over 0.4. Okay. I'm looking at frequency is 2.5. And what's the unit for frequency? Hertz. 2.5 hertz. Okay. So I'll go ahead and write that right here. 2 pi times 2.5, and that's hertz. Okay. And then times however much time is ticked along. 1, 2, 3, 4 seconds, whatever. I think that'll take care of that. Yeah. Okay. And if you want to, you could combine the 2 pi times 2.5 and get a decimal approximation. Maybe keep a bunch of decimal places. Okay. But I think that looks pretty good right there. Okay. Alright, so that's part A. Okay. Part B, what are the frequency and angular frequency? Oh, right. Well, we had to get the frequency to get this anyway. Right, so frequency is what again? 2.5 hertz. Okay. And what's the angular frequency? 2 pi times 2.5 hertz. Okay. Yeah, let's go ahead and get a decimal approximation for that. All right, so let's 2 pi. Looking at approximately 15.71. And guys, would that still be hertz? Yeah, still be hertz. Okay, because 2 pi is a constant itself. So it's the same unit. Okay. This right here, that's what this number is. Look right there. Right. Ooh, part C. What is the spring constant of the spring? Spring constant. Guys, how do you think we could find spring constant?
That one.
This one right here? This one right here? Oh, right. There should be pointing to your AP equation.
Oh, yeah.
Right. That's this one right here, isn't it? All right there. Okay. So let's try that. Let's go. Time period equals 2 pi times square root m on k. Okay. We're solving for k. How stiff is the spring? It's the spring constant. Okay. So let's put in some values. What's the time period? 0.4 seconds. Takes 0.4 seconds to cycle completely.
Oh.
And remember the mass was the first thing you told us. 1.2 kilograms. Okay. So we got 0.4 seconds equal. Equals 2 pi times square root 1.2 kilograms over the spring constant. So take the 0.4 seconds, divide by 2 pi. Okay. Guys, after you divide by 2 pi, what are you going to do? Square both sides. Okay. So maybe I'll go squared, squared. Okay. And that's equal to 1.2 kilograms divided by k. Okay. Okay. So, okay, guys, can I take k, cross multiply it?
Yeah.
And then take this squared fraction, reciprocal other side. It's got 1.2 kilograms. 2 pi quantity squared. Divided by 0.4 seconds being squared. Tell step the spring is 1.2 times 2 pi squared. Alright, you guys plug that in the calculator? Make sure you can plug that correctly into the calculator, like you're not missing any parentheses, anything like that. Okay, I've got a number on my screen. Somebody tell me what number is on my calculator screen. Somebody tell me what number is right here. Yeah.
I got it. Yeah. I got 0.60.
Nope, doesn't sound right.
Austin, your calculator is on.
Yeah. All right. I got the same thing Gunner's got, which is 296. Well, what's the unit? As a 296 what?
I'm gonna use my guess.
Unit per meter. Yeah, exactly. Spring constant. Right, that could be true, right? Here, let's check the answer. Let's check that. So let's go over here.
Yeah, I know.
Let's plug in the values. So everybody get 2 pi square root. We got 1.2 kilogram block, and we just found K is 296 Newton per meter. Those are all based on units. Time period 0.4 seconds. Oh yeah, oh yeah. All right, all right. Right, you guys good? Right, part B. What is the maximum speed of the object? Hey guys, maximum speed, there's 2 different ways to get this. 2 different ways. Guys, what's one way you guys could think to solve for maximum speed? We're going to do both ways, and I bet we'll get the same answer. Oh, did somebody say conservation of energy?
Yeah, energy kinematic.
Yeah. Guys, let's do conservation of energy.
I got the number.
Right, that's one way to do it. So, guys, let's set up sum of energy initial equals sum of energy final. Okay. So, well, here's a little diagram of what's going on.
We're doing
So, what kind of energy can determine what kind of energy allow you to solve for maximum speed? Okay, yeah, kinetic. Okay, guys, when this block is going through the equilibrium point, is there any energy stored in the spring at all? No. So where's all the energy? It's all in its what? Motion. Right. So it'd be kinetic, right? Okay. So the kinetic energy at the center would all be 1/2 mv squared. So I'll call it 1/2 mv max squared, and then we can solve for v max. Okay. Now that's just going through the equilibrium point. Okay. Now that's equivalent to energy anywhere else in the system. And where's another good place to spot all the energy? How about this maximum stretch point, or the maximum compression for that matter? And either place, all the energy is in the what? The spring. And what's the formula for that? 1/2 kx squared. And oftentimes when you're talking about the full amplitude, you'll instead of x, you'll see a for amplitude. Right? That could be true, right? Okay. Or you call it x max. That's the same thing as amplitude. Is that right? Okay. I think we have all these other values. Can we just pop them all in? 1.2 kilograms for the mass. That's what's off in. We found spring constant not too long ago. Wasn't that 296 Newton per meter?
We're trying to find the max.
And guys, what's the amplitude of the motion? In meters. 4 centimeters, but how many meters? Yeah, 0.04 meters, right? Now that we're doing math, you gotta make sure you have everything based on that units. Right? Oh, and don't forget that's also squared, right? Isn't that squared? Okay. I'll throw in the middle step here. So 1/2 times 1.2 kilograms times V max we're solving for squared is equal to, let me see how much energy is in the system at all. So 1/2 296.04 squared. I'm looking at 0.2368 joules. Okay, that many joules. Okay. I can do times 2 over 1.2 and then take the square root. Okay. Good. V max
but everything
is 0.628 meters per second. Okay. Are you guys getting the same thing? You guys checking my work? 5, 1, 2, 1.628 squared. Yeah. Yeah, that's right. Okay. Okay, so guys, here, take the 0.2368 joules. Okay. Cross multiply this 2, say times 2, divide by 1.2 kilograms. And then last step is to take the what? Square root. Right. And then that's how you get that. Okay, guys, that's one way to get the maximum speed. Can anybody think of a different way to get maximum speed?
No, I don't think there's ever another way.
Yeah,
There's no other way.
Oh, he's gonna be going forward to kinematic motion.
Right behind.
Yeah, but like, that was one that says, Oh, it's that.
How about this? Alright. Yeah, so we basically have this, don't we? If we could somehow get this, which you kind of see how to do here, right? Then whatever the maximum value is.
That's all we got this.
And guys, the maximum value, wouldn't that be for sine or cosine, whatever we have, goes to 1? Like whatever's inside here, this could max out at 1. They can tell us something about this. And then we get the same thing. You guys want to see if we did? Try it. Right, so I have to go back though. Guys, here's our position versus time. Let's make a velocity versus time. Or velocity is a function of time. So keep my amplitude 4 centimeters. I'm gonna change it to 0.04 meters, okay? Just so I don't forget to do that later. 0.04 meters. Okay. Guys, what's the if you're in calculus, you definitely know this. What's the derivative of sine? What would be cosine? Sine goes to cosine. Okay. So I'm gonna leave a little space here. So try to get your cosine of all this stuff. Actually, here, guys, wasn't this 2 pi times 2.5 just this number anyway?
Oh yeah.
So I'm gonna do that. 15.71. That's hertz. Okay. And then we still have times the variable time. Okay. But to go find the rate change. Again, if you're in calculus, I still need to apply the what rule? Chain. So what number goes right here? 15.71 hertz. Right? Guys, hertz. Isn't that the same thing as 1 over seconds?
Yeah.
What is meters times 1 over seconds? Meters per second? Which describes some kind of velocity. And cosine, whatever, that just could be a number.
Hi.
In fact, this whole piece right here could max out at what? 1. Isn't cosine bounded between -1 and 1? Right? Is that true? The same thing for sine. Like think of it in terms of the unit circle, right? Okay. So V max would be where would correspond to all this cosine whatever just being equal to 1. Okay? Okay. And that's gonna tell us something about the peak of this curve right here. Okay. So I think the answer is just whatever this comes out to. 0.04 meters
Everything over here.
times 1571 hertz.
So we don't do. Log in and up. I do like this.
0.628
And then what's left?
meters per second. B max. Okay. Well, that's what we got for this point of view. I forget what we got before. You guys remember we did conservation of energy a few minutes ago? Okay. Let's see. See what we got for. Got it.
The same.
Is it the same?
Yeah, I know.
Oh, maybe it's on 0.628. Oh yeah, it is the same. Oh yeah. There's conservation of energy. There's the oscillation formula. It's the same D max. Alright, you guys good? It's the same. Alright. Here, guys, this last one we'll just we'll just do this last one verbally. Okay. Guys, what's the maximum acceleration? Well, guys, if we found maximum velocity, do you see the procedure to find maximum acceleration? You just take another rate change. Okay. Now, guys, here's the big pattern. So the rate change in cosine is negative sine, the rate change is cosine, right? But you guys know if you're trying to maximize, like find the maximum value. Here, guys, focus here. If you're trying to find the maximum value, what is sine or cosine of whatever? You can just set this equal to what? We just did it. One. Right? But every time you take a rate change, you guys see what comes out one more time, gets multiplied one more time? Is this angular frequency, which is 2 pi f? Is that? Okay. So then if I took out another 2 pi f, right, I could just do that again too. Right. Actually, that might be all you have to do. Guys, if you take this, okay, I'm gonna make this claim. A max equals 0.628 meters per second times 15.71 hertz. 9.87 meters per second squared. There you go. That's the answer. Okay. Because you just keep taking on another angular frequency, don't you? Oh yeah, that interestingly is pretty close to 1G. Yeah, guess coincidentally, right? All right. So you got next here. Number 2. It says the period. They're talking about the time period. Yeah. The time period of a simple pendulum is capital T, and we increase the length so it's 4 times longer. What will the new time period be? Number 2. Pendulum. Swing. Take some time. Here, maybe you guys have this one memorized by now. Guys, what's the time period for a pendulum? 2 pi times square root. Energy. That's okay. Now they gave us no numbers here, but they gave us a proportion. They said the length is 4 times longer. Let's say this is the original time. Well, no, here, I'll write the same format here. Let's do it this way. 2 pi square root L over G. Great. So I wrote the same thing, right? Okay. Price. Here's what I'm gonna do. I'm gonna say this is the original down here. Guys, that's the original now. Okay. And we'll make this the new time period. Right? But the new time period, I'm gonna slap a 4 on that L. So make it 4L. Okay, you guys do the same thing? Now if you divide one by the other, what's T new compared to T original?
2.
What cancels?
Everything.
Yeah, almost everything.
Everything. Oh my gosh.
Except for that's square root of 4. Which is what? 2?
Max equilibrium minus max. Right. Perfect.
Right.
Did it for okay.
But oftentimes, you guys have done so many of these proportions. You probably saw that from the beginning anyway. Right? I could have just said this. If I slap a 4 on that L, you take the square root of 4 is 2. You say, oh, 10 times twice as long. Right? You can see it. Right? But this was a free response question. Maybe you want to show your work, and that'd be one way to show your work. So 4 times the length.
That's really wasn't a question, but we just did.
That's 5. Let's say it's 4 times the length. It's like 4L. Right? But it's 4 times the length. It takes twice the time. All right, you guys got 4 times the length first time? Okay, number 3. Simple pendulum. Surface of Earth is 1.24 meters long. Oh, what's the angular frequency of oscillation? Huh. Let's figure that out. So they gave us L is 1.24 meters. And, well, I guess we know G can be 9.8 meters per second squared. Pendulum going, yeah.
And then some read.
So let's solve for time period first. Time period is 2 pi root L over G. L of course is 1.24 meters.
We have the number.
G is 9.8 meters per second squared.
That is the law. Yeah, he did solve this. That's not physical.
Yeah.
I thought it.
Okay, so that's the time period. Okay. That wasn't their question though. Your question was angular frequency. So let's find regular frequency. Guys, what's the formula for regular frequency? Yeah, 1 over t. All right, let's go ahead and get a number for that. So I can just hit the key. It says x minus 1.
1 over t.
To take the reciprocal, so it's a reciprocal. So 0.4474. What's the unit on that? Hertz. Okay, so now we got that. Okay. Now angular frequency. How do you get angular frequency? Yeah, 2 pi times the regular frequency. So all we have to do is this times 2 pi. So times 2 pi.
I don't feel like time is my 2.8.
That's angular frequency. Yeah, what's the use of angular frequency is that if you want to describe the motion or like the position of the bob as a function of time, then that would be a good step to do.
Why would you leave the keys in the trash can?
I mean, I smacked it. My mom. Oh, that's
You guys, here, let's do a little side. Are you guys okay so far? You guys got that? Okay. Here, I want to do a little side thought here, because based on what I just said, like if you want to know the lateral position of this bob, is that very similar to how far it's physically moved, like along this arc? Only if what?
Only
if it's small. Here, guys, watch this. Everybody pull up your calculator. Switch it to radians. So see DRG. Hit DRG and switch it over to radians. We'll switch it back later. Just switch it to radians real fast. Okay. Is everybody's calculator in radians now?
It's on radians.
Yeah.
Everybody's calculator is in radians. Right, I'm going to show you guys something called the. Well, I've heard it called the small angle theorem. Okay. And so theta in radians. This only works for radians. Okay. Guys, hit sine. Hit sine. Okay. And no, you guys know.
Smaller angle equals a bigger.
Actually, let's put that a minute. Let me get some numbers on the board. Let's go 0 degrees equals 0 radians. You guys know that. Guys, what's 90 degrees?
1
Pi over 2
Oh,
radians. Okay. What is pi over 2? That's about 1.5. About 1.57 radians. Okay. Guys, what's 30 degrees? Would that be a third of that?
32 of the.
Okay. 30 degrees is about 0.52 radians. Okay. Now anything smaller than 30. Here, let's divide that by 3 again. Okay. 10 degrees is approximately 0.17 radians.
I think he was like,
Okay.
oh, that's
So
not that
remember, your calculator's still in radians. Let's go sine of. Let's go 0.05 radian.
Of them.
Sine of 0.10 radians.
I think that was
Sine of.
Well, we
Let's go. Let's do 0.52 radians. Okay.
Hold on.
Let's do
You did this.
let's go 1 radian. It's about 57 degrees. Okay.
No way.
Let's throw in one more.
Please stop explaining. I bet neither of them are.
Okay, you guys ready to make some calculations with me? You guys, something really cool comes out of this. You ready for this? Sine of 0.01. You guys got sine of 0.01? So that's a very small angle. Isn't that like maybe close to a degree? Right, so close to a degree on the protractor, just very, 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 very tiny. Right, very small angle. Right, this is called small angle theorem. What do we see here? 0.00999998. Is this? Hey, that looks like that number, doesn't it? That's basically the same thing. Huh? How about 5?
Maybe like this.
0.049979. Hey, that's basically that number. 0.09983. Hey, that's basically that number.
I was the one who said it. Okay, that's the great guess.
Here, you guys see you guys see what I'm trying to show you here? What am I showing you here?
Like that one?
Yeah, for small angles.
Oh, that's
Let's say where does it kind of drift off? Probably around 30 degrees. Now it's starting to kind of drift off. Okay. So let's say theta is less than 30 degrees or 0.5 radians. You know, somewhere in there. Those are pretty close to each other. Okay. The angle is approximately equal to the sine of the angle. Okay. Again, this only works for radians. It has to be in radians.
Stop looking at my ninja secret.
Here, what do we see? How about we probably have time for one more. So it would be a good one. Here, let's do number 2 right here. You guys see this number 2? It says show that these are dimensionally correct. So E equals 2 pi times square root of m over k. Let's start with that. Here, guys, write this down. Here's a pen. Okay. Guys, what's the unit for time? Seconds?
No, apparently T for
Seconds? So here, we're just gonna write in terms of units. But the numbers don't matter anymore. So guys, 2 pi. Are there any units on 2 pi? No, it's just a number. Okay. So we got square root. What's the unit for our mass? Kilograms? Let's put kilograms. What's the unit for spring constant? Yeah, newtons per meter. This is pretty wacky. Guys, do you think this whole thing on the right simplifies to seconds?
Yeah, sure.
Let's see if it does. Because, okay, square root, got a fraction. Okay. Well, a fraction within a fraction. So here, I'm going to keep kilograms on top. Guys, can I take that meters down here and flip that up on top also? Meters. Okay. And what does newtons break down into? Kilogram meter per second squared? Yeah. For Newton's second law of motion, F equals ma. That's kilogram, meter, and then per second squared. Can the second squared flip back up on top? That could be like that, couldn't it?
Hey, I wonder what's gonna cancel out.
And that's what it's
The seconds equal to the square root of second squared? Oh yeah. Oh yeah. That was 2a. Let's try 2b. That was a. Here's b. Okay. Time period equals 2 pi times the square root of L over G. So time periods in seconds. 2 pi is just a constant. Square root. Got meters here. Got meters per second squared. So second. Find this. Square root of meters times second squared over meters.
Wow. Seconds equals seconds.
That's pretty easy. There you go. Alright, that's alright, right? Alright, you guys got all the notes for today? or got those all on paper? Right, so if we have time next week, of course I'll do more with the guys. Right, guys, do some AP classroom over the weekend. If you want more practice, we got a lot more puzzles in that pack right there. Everybody turn in their lab from yesterday. Close on the week.